All right, guys, here we go. Can I get a thumbs up at home that you hear me and see the board okay? Awesome. All right, so guys, still working with these inverses. Yesterday, I just kind of, like I said, I wanted to take that day to kind of make inverse sine feel a little bit better in hopes that now when we go to the other inverses, you'll be able to work with them a little bit better as well. All right, so today we're going to do the inverse cosine. So remember, in general, the trig functions, guys, your attendance, they called for your attendance.
Yeah,
okay.
I was up there.
That's fine. The trig functions, they're not one-to-one functions. By definition, they should not have an inverse that exists unless we restrict their domains to just a portion of their graph, and then we can force the inverse to exist. But it only exists for that portion of the graph that survived the cut. So again, it's going to limit the angles that it's going to be capable of spitting out of its inverse, okay? So let's look at the cosine graph to see where did we cut it? What portion of its graph survived the cut, okay? So remember, with the cosine function, an angle goes in as x, and it spits out a ratio. So we can plug any angle we want into the cosine function and take the cosine of it. And then a ratio between -1 and 1 is what it is capable of spitting out. Because remember, the ratio for cosine is a over h. It's an x-coordinate over a radius. The a is always smaller than the hypotenuse. The x-coordinate is always smaller than the radius. So it's always a small number divided by a big number, which will always result in a number between -1 and 1, okay? All right, so look at how he works. You plug an angle between 0 and pi over 2 in, and a ratio between 1 and 0 comes out. You plug an angle between pi over 2 and pi in, and a ratio between 0 and -1 comes out. You plug an angle between pi and 3 pi over 2 in, and a ratio between -1 and 0 comes out. You plug an angle between 3 pi over 2 and 2 pi in, and a ratio between 0 and 1 comes back out. And now everything starts to repeat after that. Okay, so if I want his inverse to exist, right now, he does not pass the HLT. There are way too many angles that make the same ratio came out, right? 0 makes a ratio of 1 come out, 2 pi makes a ratio of 1 come out, -2 pi makes a ratio of 1 come out. So right now, if I took the inverse cosine of 1, it could spit out this angle, it could spit out that angle, it could spit out this angle. It's not a function. So we have to cut it to make the inverse exist. So a good place to start when you want to keep a portion of the graph is 0, right? Let's start right here. So guys, at 0, the graph starts up here. So if you think about it, if I'm going to go to the right and only think of it to the right of 0, it's like, yeah, it's passing the HLT if we just look directly right here. But if I tried to go backwards, it wouldn't pass the HLT anymore, which means I'm not going to want to go backwards. I'm going to cut it right at 0. I'm not going to go past 0. All right, and then it's kind of like, all right, it's passing the HLT, it's passing the HLT. Yes, 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 yes. Then you get down to here, and as soon as it turns back up, it ain't going to pass the HLT anymore when it hits this curve. So that means we're going to have to chop it also right here before it turns and comes back up. So the portion of this graph that we keep is going to be from 0 to pi. Those are the angles that survive the cut of the cosine's graph to make the inverse cosine exist. So if you look at this right now, angles from 0 to pi survive it, and ratios from 1 to -1 survive. So yet again, all the ratios survive the cut, but only the angles from 0 to pi survive the cut of its graph. So the inverse cosine is only going to be capable of spitting out the angles that survived. Angles from 0 to pi. Quadrant 1 and quadrant 2 angles survive his cut. All right, so let me move mine up so I can fill that in. I don't think I can do it. All right, so does this graph have an inverse that exists? Technically, no, it didn't at first, but then we can restrict the domain to only a portion of it. We're going to take a smooth, continuous portion of the graph where it exists, and we saw if we restrict the domain from 0 to pi, then the inverse can exist. So the x values, where 0 less than or equal to x less than or equal to pi. If we keep x from 0 to pi, it can exist. Therefore, the inverse function only exists for angles in between 0 and pi, which are quadrant 1 and quadrant 2 angles. Okay, so let's create a cheat chart for the inverse cosine. As far as the inverse cosine is concerned, right, he only has angles from 0 to pi surviving. So this is the portion of the unit circle that survives the cut of his graph, right? Angles from 0 to pi. Quadrant 1 or quadrant 2 angles. All right, well, guys, think of the angles that are good to us that survived the cut, right? We got 0 radian sitting here at 1, 0. We got pi over 2 survived sitting at 0, 1. We got pi survived sitting at negative 1, 0. And then think about your specials, your 30, your 45, and your 60. Pi over 6 survived, our 30 degree. Pi over 4 survived, our 45 degree. And pi over 3 survived, our 60 degree. And then any multiple of them that landed in quadrant 2 survived. So guys, what multiple of pi over 6 survived over here? Well, 1 pi over 6, 2 pi over 6, 3 pi over 6, 4, 5. Your fifth pi over 6 survived. So that's an angle that the inverse cosine is going to be capable of spitting out. Well, what multiple of pi over 4 survived? 1 pi over 4, 2 pi over 4, 3 pi over 4. 3 pi over 4 survived the cut of the graph. That's a good guy for us. And then your 60. 1 pi over 3 and 2 pi over 3. Your 120 degree angle, 2 pi over 3 survived. So as far as the inverse cosine is concerned, these are the good guys. All right, and then look over here. Actually, you know what? I don't want to fill that one in yet. I want to do the graph of the inverse cosine first. All right, and then just don't forget, all students take calculus. So there are angles that create the same ratio in two quadrants. So this is where all angles produce a positive ratio, right? So the cosine of an angle in quadrant 1 gives you a positive ratio. The cosine of an angle in quadrant 2 gets you a negative ratio. Only sine is positive. The cosine of an angle in quadrant 3 gets you a negative ratio. Only the tangent ratio is positive for angles in quadrant 3. And then the cosine of an angle in quadrant 4 is positive. Only the cosine ratio is positive for angles in quadrant 4. Well, guys, remember, the cosine is only capable of spitting out angles between 0 and pi. So if you get an angle in quadrant 4, you're going to have to convert that to a quadrant 1 angle, because that's where he would have another angle that produces the exact same ratio. All right, and then if you end up with a quadrant 3 angle, inverse cosine is not capable of spitting out a quadrant 3 angle. You're going to have to convert your quadrant 3 angle into a quadrant 2 angle, right? That gives you the same ratio. All right, I'm going to come back to this one. Because the only problem with this is that I can't leave stuff on the board. Okay?
Did you do anything with this middle?
No, I'm leaving that blank. I'll come back to that. I want to do this first before I fill that in. All right, so here we go. Let's see how the inverse cosine graph looks then. So guys, remember, to create the inverse, we started with the cosine function, y equals cosine x. You switch x and y, and there's the inverse, right? That is the implicit version of the inverse. It's just not solved for y, right? So we want to solve it for y and create the explicit form of the inverse. Well, how do I undo cosine and get y by itself? I inverse cosine it on both sides, and you're left with y equals the inverse cosine of x. So now you plug a ratio into the inverse, and what ratios survived the cut? All of them. Ratios from -1 to 1, right? A ratio goes in as x, and then an angle is going to be what comes out of the inverse cosine as y. But guys, not any angle, only an angle that survived the cut. And only angles between 0 and pi survived the cut of its graph. So it's only going to be able to spit out an angle between 0 and pi. All right, so a ratio between 1 and -1 can go in, and an angle between 0 and pi can come out, which means right smack in the middle, pi over 2 survived. Okay, so guys, if you can picture the portion of the cosine curve that survived, right? This was the angle 0 and a ratio of 1 came out. So now a ratio of 1 goes into the inverse and an angle of 0 radians comes out. All right, this was pi over 2, 0. An angle of pi over 2 went in and a ratio of 0 came out. Now a ratio of 0 goes in and an angle of pi over 2 comes out. And then last, when pi went in as the angle, a ratio of -1 came out. So now, when a -1 ratio goes in, an angle of pi radians comes out. And you kind of are left with like a curve that looks like this. Now, my spacing is absolutely terrible. It's actually much taller. It probably looks something a little bit more like that. I just didn't space it correctly if you were ever to Google the image. All right, but this gets the job done. So guys, look, this is saying, if I plug a ratio between 0 and 1 in, if I plug a ratio anywhere between 0 and 1 in, an angle between 0 and pi over 2 comes out. So that means the angle would be in quadrant 1. So you would put the triangle or put the angle in quadrant 1. If you take the inverse cosine of a positive ratio between 0 and 1, it's spitting out your quadrant 1 angles. And then it says, if I plug a ratio between 0 and -1 in, guys, if I plug a ratio between 0 and -1 in, an angle between pi over 2 and pi comes out, which are my quadrant 2 angles. So when you take the inverse cosine of a negative ratio between 0 and -1, it's going to spit out your quadrant 2 angles. So you would put that triangle or you would put that angle in quadrant 2. So the positive ratios get you your quadrant 1 angles. Your negative ratios get you your quadrant 2 angles. So guys, without moving this, that middle graph that I left blank, that middle graph, right, with the third quadrant crossed out, because I kind of warned you, quadrant 3 angles don't survive the cut of any trig functions graph. This now means if you take the inverse cosine of a positive ratio, you're going to get a quadrant 1 angle. If you take the inverse cosine of a negative ratio, you're going to get a quadrant 2 angle. That's kind of like your cheat chart for the inverse cosine. Inverse cosine positive ratio, quadrant 1. Inverse cosine negative ratio, your answer is a quadrant 2 angle. All right, let's try some problems. Okay. All right. Here we go. All right, so guys, you know 2 inverse functions right now. You know inverse sine, he's capable from pi over 2 to negative pi over 2, quadrant 1, quadrant 4. And now you know inverse cosine. He's capable of quadrant 1 and quadrant 2 angles, so 0 to pi. So you have to remember which inverse you're working with and what angles they are capable of. All right, now that we know more than one, it can get a little confusing. All right, but we're doing all inverse cosine. I apologize about my blue lines, it's my spacing. All right, here we go. Find the exact value of the inverse cosine of 0. Well, guys, think about this, right? You take the inverse cosine of a ratio, we know the answer is an angle, right? We know the answer to this is an angle. The inverse cosine is only capable of spitting out angles between 0 and pi. So that's what we have to do. We have to give an answer between 0 and pi. So think about what, if they're going to ask you to find an exact value, it's special. It's somewhere that survived. It's a good guy that survived the cut. So we got 1, 0, 0, 1, -1, 0. You're really trying to find out the cosine of what angle had a ratio of 0. So guys, what angle who survived the cut of the graph had an x-coordinate of 0? Because that's the cosine of that angle. What angle has an x-coordinate of 0? Pi over 2. So that means the inverse cosine of 0 spits out the angle pi over 2, because that's the angle who had a ratio of 0 that survived the cut. All right? What if we have to find the inverse cosine of negative root 2 over 2? All right, guys, we know the inverse cosine of a negative ratio is going to spit out a quadrant 2 angle, right? Inverse cosine can only spit out angles between 0 and pi. We just saw on the graph that if you took the inverse cosine of the negative ratio, it's spitting out a quadrant 2 angle. So now you got to figure out what special angle had a ratio of root 2 over 2. Was it a 30, a pi over 6? Was it a 45, a pi over 4? Was it a 60, some version of pi over 3? Who had the special ratio of root 2 over 2, right? The cosine of what angle had a ratio of negative root 2 over 2? So guys, look at your triangles. Does anybody know the cosine of what angle, 30, 45, or 60, had a ratio of root 2 over 2? Anybody know? It's a 45. So guys, this is definitely a 45-degree angle of some kind. All right, but here's the answer. It can't be pi over 4, because pi over 4 is a quadrant 1 angle. You have to figure out what multiple of pi over 4 landed in quadrant 2. So guys, remember, in the world of pi's over 4, here's 4 of them. So what's the one that landed right before it? 3 pi over 4. So it would spit out 3 pi over 4. That's the multiple of a 45-degree angle that landed in quadrant 2. Does that make sense? Is everybody okay with that? Okay. All right, what about the inverse cosine of root 3 over 2? Guys, we know if we take the inverse cosine of a positive ratio, it should spit out a quadrant 1 angle, right? Inverse cosine is capable of spitting out angles from 0 to pi. If the ratio is positive, it should spit out a quadrant 1 angle. So now you have to ask yourself, the cosine of what special angle had a ratio of root 3 over 2? Was it a 30? Was it a 45? Was it a 60? Anybody know the cosine of what angle was root 3 over 2? Look at your triangles. It's a 30, which is a pi over 6. And does pi over 6 land in quadrant 1? Yes. So that is the quadrant 1 angle that had a ratio of positive root 3 over 2. All right, and then the last one. The inverse cosine of negative 1/2, right? We know if we take the inverse cosine of a negative ratio, it should spit out a quadrant 2 angle. The inverse cosine is capable of spitting out angles between 0 and pi. It should be a quadrant 2 angle. Okay. Well, now you have to figure out what special was this. They don't want me to use a calculator, so it should be some form of a 30, 45, or 60. So the cosine of what angle equals a ratio of negative 1/2? Anybody remember who had a cosine ratio of 1/2? 30, 45, or 60? It's a 60, which is pi over 3. But guys, does pi over 3 land in quadrant 2? No, he lands in quadrant 1. So in the world of pi's over 3, 3 of them brings you to there. Who's the one right before it? What is it? Not 5 pi. 5 pi would be over here. If this is 3, who's the one right before it? 2 pi over 3. And you're done. And 2 pi over 3, guys, it's 2 times 60. It's 120. It definitely lands in quadrant 2. All right? So again, the nice thing about inverse sine is it worked with quadrant 1 to quadrant 4 from pi over 2 to negative pi over 2. So you never really had to worry about multiples of any of them because they were either pi over 3 or negative pi over 3, or pi over 6 or negative pi over 6. Quadrant 2, you got to figure out what multiple of your special landed, so it gets a little bit trickier. All right, now the compositions. Okay, let's look at the first one. The inverse cosine of the cosine of pi over 12. Well, guys, think about this. You take the cosine of an angle, the answer is a ratio. You take the inverse cosine of a ratio, and the answer is an angle. We know the answer to this question has to be an angle. So guys, in reality, what does the inverse cosine do to the cosine function? It cancels it, and I'm left with the angle that I started with, as long as that is an angle that the inverse cosine is capable of spitting out. Guys, is pi over 12 an angle that landed in quadrant 1 or quadrant 2 between 0 and pi? Well, think about it. If this is pi's over 12, here's 12 of them. Half of them would be 6 of them. Where's 1 pi over 12 going to be? right there in quadrant 1. So that's definitely an angle that this function is capable of spitting out. So pi over 12 is definitely our answer. Okay? All right, I'm going to skip B because I think he's the hardest one, and I kind of wish I didn't put him next. So let me just go to this one first. All right, the inverse cosine of the cosine of negative 2 pi over 3. All right, well, here we go. You take the cosine of an angle, you get a ratio. You take the inverse cosine of that ratio, and you're going to get an angle. We know the answer to this question is going to be an angle. All right, so the inverse cosine and the cosine cancel. I should be left with that angle. As long as that is an angle that the inverse cosine is capable of spitting out. Guys, anybody know where negative 2 pi over 3 lands? Quadrant 3, right? Here's negative 3 pi's over 3. Here's 0, right? This would be negative 1.5 pi over 3. Negative 2 pi over 3, guys, he lands in quadrant 3. The inverse cosine couldn't possibly say that was the answer. That's not an angle that survived his cut. So remember, all students take calculus. It's positive, negative, negative, positive. So your negative angle, we're going to convert him to the quadrant 2 angle that gets us the exact same ratio. So guys, we got to move this into quadrant 2. All right, to do that, you need your reference angle. Guys, how many pi's over 3 live in between negative 2 pi over 3 and negative 3 pi over 3? That's 1. All right, so that means the reference angle is 1 pi over 3. So then if this is 1 pi over 3, this is 1 pi over 3. But you can't say that that's the answer because pi over 3 isn't a quadrant 2 angle. So guys, that's your reference angle. But who's this angle that had the reference angle of pi over 3? How many pi's over 3 are right there? Anybody know the answer? 2 pi over 3, right? That's the quadrant 2 angle that had a reference angle of pi over 3. So that is 2 pi over 3. You have to use your reference angle to figure out what multiple of that pi over 3 landed in quadrant 2. So the angle that he'd be capable of spitting out to this question is positive 2 pi over 3, because that's the quadrant 2 angle that survived his cut. All right, now let me go back to this one. Okay. The inverse cosine of the cosine of 11 pi over 9, right? That's a 9? I can't read it. Okay. All right, we know if you take the cosine of an angle, you get a ratio. If you take the inverse cosine of a ratio, the answer is an angle. The answer to this question is definitely an angle. So the inverse cosine and the cosine, they cancel. I'm left with that angle. As long as that angle is an angle that this function is capable of spitting out. So where the hell do 11 pi's over 9 land, guys? Quadrant 3, right? Here's 9 pi's over 9. Where's the 11th one? Well, guys, half of 9 is 4.5. So this is 13.5 pi's over 9. So 12 of them is definitely here. It didn't make it past the halfway mark. So here's 12 pi's over 9. Oh, 11. Good call, Kate. I'm like, wait, that reduces. Why did I put that? Good call. All right, so guys, we got any quadrant 3 angle, right? Positive, negative, negative, positive for cosine. Quadrant 3s need to become quadrant 2s because there's an angle in quadrant 2 that will get us the exact same ratio as this angle. All right, so guys, who's your reference angle? Between 11 pi and 9 pi. All right, 2 pi over 9. So now give yourself a reference of 2 pi over 9 in this quadrant. So what angle are you really at if you're 2 pi's over 9 short of 9 pi's over 9? 7 pi's over 9. 7 pi's over 9 is the angle that he would be capable of spitting out for this question. And if you do this, guys, if you plug this into your calculator, the inverse cosine of 11 pi over 9, hit enter, it gives you the decimal version of this angle. Okay? Go ahead, question?
Yes, I'm a little confused on where'd you get the 2 pi over 9?
It's our reference angle, right? If we're working with pi's over 9, we know this is pi at 180 degrees. That's 9 pi's over 9. So if we were sitting at an angle of 11 pi's over 9, there were 2 pi's over 9 in between them. That's our reference angle, the angle between our angle and the x-axis. So that means we have to create an equivalent angle in quadrant 2 that not an equivalent angle, an angle that gets you the equivalent ratio, which means it would be the angle that has the same reference angle. So if this is a reference angle of 2 pi over 9, then we have to build a reference angle of 2 pi over 9 in quadrant 2, and then figure out what angle I'm really sitting at that had a reference of 2 pi over 9. So we got 2 pi over 9 by figuring out what was left in between the 9 pi over 9 and the 11 pi over 9.
Okay.
Okay? All right. I'll do this one on the notes for you. This one, I believe, is a quadrant 4 angle that you have to convert to a quadrant 1 angle. It's pretty easy. But let me do these ones. If I have time, I'll come back. All right, guys, look at the reverse composition. Now you're taking the inverse cosine of a ratio, and the answer is a angle. You take the cosine of an angle, and the answer is a ratio. But remember, only ratios between -1 and 1 can come out of the cosine. So that's the only thing it would be capable of spitting out. So guys, the cosine and the inverse cosine cancel. You're left with a ratio of -3/4. Is that in between -1 and 1? -3/4. Yeah, so he's a good guy. So -3/4 is definitely the answer to this question. All right, same thing here. You take the inverse cosine of a ratio, you're going to get an angle. You take the cosine of an angle, you're definitely getting a ratio. But only ratios between -1 and 1 can come out of the cosine function. So could the cosine function spit out a ratio of 1.5? No. So this is an undefined. He's a bad ratio. Right? Ratio is greater than 1. That's not good. I'm going to try it, guys. Why not? We're moving. The inverse cosine of the cosine of -pi/4. You take the cosine of an angle, you get a ratio. You take the inverse cosine of a ratio, and you get an angle. Okay. They should cancel, and you're left with that angle. As long as it's an angle between 0 and pi, we're good. So guys, where's -pi/4 land? In quadrant 4. So remember, all students take calculus. All calculus. It's positive in 1, and it's positive in 4. So quadrant 4 angles have to become quadrant 1 angles. So guys, who's your reference angle here? Pi/4. So give yourself a reference angle of pi/4 in quadrant 1. And who's got a reference of pi/4 in quadrant 1? Pi/4. So pi/4 is the angle he would be capable of spitting out. And that's the answer. Does that make sense? Are we okay? All right. All right, so guys, I gave you inverse cosine homework today. I actually ended up making it due tomorrow because it's just questions like this, so they don't take a super long amount of time. But if there's an issue and this due date was too quick, just let me know. I can always extend it till Friday. All right, but you do have a homework assignment on this. Try to get it done by tomorrow night, okay? I will see you guys tomorrow, and I hope you have a wonderful day. Let me know if you have questions. Sorry, guys. One day I'll fit this into a 30-minute class.